kind of light today. Anyway, so I think I'm up to date with looking at your materials. I can't remember exactly when the next deliverable is. I guess the last one is the end of week 7, which was a week before spring break, and so end of this week, I guess. So I guess this Sunday must be the deal here, which would be the end of this coming Sunday. There is some leeway in these because you have 2 weeks to be able to prepare quiz questions, and so nothing's going to be done with these things as you upload them. So, but if you are keeping on schedule, that's great. I think we probably had 75% of people submit by week 7, kind of on time, and I went through those. In terms of where we are, we're just after spring break. So spring break is an 8-week and 7-week part of the semester for 15 weeks total. And so now we're a fair way through here. We've talked about thermomechanical properties or thermophysical properties of the subsurface, and conduction of heat in the subsurface, thermodynamics of phase change, which is a big thing for geothermal reservoirs. We've talked about mechanisms of subsurface fluid transmission for multi-phase fluid and some simple models that we could use. We've talked about the implications of geochemistry in terms of the occlusion of permeability or the dissolution of components, the importance of retrograde and prograde reactions and how different things will occur within the reservoir. We've talked about different methods of characterization, in situ methods, drilling and geophysics, and just where to expect these hydrothermal deposits being accessible. And so now we're on the final strip, which is kind of the applications of all these principles to hydrothermal reservoirs, which we know are the reservoirs which are maxed out. Not many portions available for all the sweet spots have been taken, and we'll talk about that today. We'll talk about heat from sedimentary reservoirs, lower heat, maybe used for district heating. We'll talk about EGS in terms of enhanced geothermal systems and what those represent. We'll talk about direct use. We'll talk about the big place for jobs, I would think now, would be ground-sourced heat pumps. All the other geothermal domains, I think, are quite niche and quite specialized, but ground-sourced heat pumps have become a huge thing. And then we'll talk about underground thermal storage. So I did go through and revise this schedule, and so I don't know whether you're happy to know or sad to know that this is our penultimate meeting time. We'll only meet one time after today. And so if any of you turned up last time, this was the deal here before spring break. So we're meeting today, it's the 17th. On the other occasions, then most of the things will be cameos by different people we invited in. It was in the year after COVID, so it was spring of 2021. You already have listened to Justin Pugnacek, who's in Belgium, working on kind of sedimentary, shallow geothermal deposits below the boom clay. You've heard already from Will Pettit, who was talking about the use of oil and gas technology to be able to pull out geothermal energy in EGS, which is now what is happening 5 years after he was talking about that. At the end of this week, you have 2 assignments. I think they're quite easy assignments because I think the quiz box is as to whether you've looked at it or not, and so you can probably game that one as you wish. But Jim Folds will talk about play fairway analysis, so how you use maybe aerial photography, satellite imagery, to be able to look for the structural characteristics that would tell you whether there's a geothermal a hydrothermal deposit at shallow depth below the surface. Greg Bignell in New Zealand, who will talk about the New Zealand geothermal fields. He is someone who worked in research for a while and then switched over to Capital Energy. They work on small binary conversion units where you take low temperature fluids, less than the boiling point of water, and you put it through somewhere where you can vaporize a low boiling point fluid, such as isopentane, that will vaporize and run through a turbine in a closed cycle. And so you can generate electricity from units where the output of the geothermal reservoir is less than boiling. In week 10, talk about sedimentary geothermal reservoirs. I'll get you to look at 2 cameos of me, here and here. In the following week, again, you'll look at stuff online, some presentations at meetings by myself and by Joel Moore. Joel Moore was, I think he just retired as the principal investigator of the Forge EGS project in Utah, a $150 million Department of Energy demonstration project for geothermal energy in rocks which previously are not permeable, so not hydrothermal. And then after that, Patrick Fulton will talk about the Cornell EGS project and its projection for direct use to be able to limit the burning of natural gas. They converted, just like Penn State, they converted their campus from coal, as Penn State did maybe 15 years ago, to natural gas. So the plant that sits on the corner of Burroughs and College Avenue burns natural gas to heat water and steam for direct use on the campus. Cornell have done the same thing. They've transitioned from coal to natural gas. I think they also burn chicken poop as well as a bio material. But they also now want to replace the natural gas with direct heat from a deep geothermal well, which is under construction. And actually they cool their campus in the summertime by cold water that's drawn, I think, from the base of the lake that's next to them, I think Lake Cayuga. You'll be back with me for heat pumps, so I guess I will be back on the 14th of April. So from the 17th of March to the 14th of April, we're not in the classroom. And then Sid Green will talk about underground thermal storage, and then that'll be the end of it. So that's kind of the progress we have. And I just mentioned that at the end of this week, this is the next deliverable, and then questions. And then after this, I'll start uploading your videos and questions online so that you can individually go through them and view them and learn from them, hopefully. And so that's kind of the layout of the class. And so these deadlines, as I mentioned, aren't so important, but certainly the final deliverable one is, because I need to be able to upload them for you to do that. And that's about it. So that's where we are. So just so you don't accidentally turn up again, I guess. I was going to say what I said anyway. I only found out an hour ago that some of you turned up from fun. Okay. So we're working our way through these different deployments, I guess, if you like, for geothermal energy. The most iconic, I suppose, is hydrothermal. Only exists on plate boundaries. Destructive plate boundaries like the geysers in California, constructive plate boundaries like Iceland. And we've talked in large part about the mechanisms of recovering heat from the subsurface. So what we'll talk about today in regard to hydrothermal plants is we'll talk about plants and their layout, which I don't know much about, but you'll learn much more on Thursday from Greg Bignell, whose talk from Baseload Energy is exactly about that. We'll talk about how to evaluate the masses that we can recover, or mass rates that we can recover wells. We can talk about parasitic losses in well bores. Of course, if you're pulling fluids up from a well and it's not driven by artesian pressurization, you have to pump, and that's of course a cost that you have to apply to the net economics of these sites. And then we'll talk about the thermodynamics of energy conversion. So in other words, when you flash hot water to steam and use that steam to run through a turbine and generate energy from the phase change developing into electrical energy, and that could be either single or dual flash, or as we just talked about, binary production, where you can actually produce electricity from fluids that come out of the subsurface which are less than boiling point and that don't flash to steam. So we started this class off in talking about the kind of global energy balance. I guess we live on a 10 to 15 terawatt planet. I'm guessing that the US uses about 20% of that, so that's 2 to 3 terawatts capacity in the US. And if you look at the sources of geothermal capacity, this also comes out of Glassey's book. This would be 1970, this would be the oil shocks of 1973, when OPEC was formed and shut down supply, actually not so different from now in a different context, to be able to limit oil supply. And the Arab oil shocks occurred, coal went into a resurgence, but also it seems here that the big grow out of geothermal energy occurred there. If you look at the growth in it over the last, in this case, 20 years, from 1995 to 2012, if you look at the US, the geysers, as we talked about before, is something like a gigawatt. So this is 3,000 kilowatts, so this is 3 gigawatts. But I guess the most striking feature here is if you look at the US, in 20 years, the main capacity in terms of geothermal, only really hydrothermal, has been something like 300 kilowatts, no, 300 megawatts. So a big thermal power station is about a gigawatt. So this would be 3 thermal power stations. And so this is a relatively small proportion, of course, of this. So 3 terawatts versus 3 gigawatts is 1,000th. So 1,000th or 0.1% of the capacity of power in the US is from geothermal. So still a niche source, but so places that are notable that we've seen before, 600 megawatts in Iceland for a population which I think is only 500,000 in Iceland, very small country. Japan would stand out as being a place with a great need for geothermal energy because they have no natural fossil resources. Neither do Iceland. Apparently before the 1950s, when they decided to go to hydro and geothermal, Iceland was smoggy because their power supply came mainly from burning peat, which has a high carbon loading to it, and also particulate loading. So anyway, a rough size of the geothermal capacity place-wide. These come from Greg Bignell's talk, which you'll see later on, and it's just to lay out the general architecture of a geothermal field with some pictures. So typically a field will contain a number of wells. We've seen some pictures before, I guess not included here. And those individual wells will supply the main geothermal plant. And so incoming hot water and steam coming from a single well here, would come into something like this, a separator. And so the separator would be taking hot water and steam in here. It would open up in this vessel. The steam would be buoyant and rise to the top and be scavenged off and into the turbines, taken to the turbines. The water would be a liquid. It would sit at the base of the tank and be scavenged off and then be taken to be potentially reintroduced to keep the pressure in the reservoir high and to keep the temperature in the reservoir high also. And so the stuff that goes to the turbines would end up, not this, in a turbine hole, and the basic makeup of those occurs further down here, but perhaps it's useful to see exactly what they look like. That's the same picture as before. And a turbine, you saw some of them earlier on, orange cowled things at Huntley Power Station, which is a thermal power station. But here, the turbine hole would contain a turbine with a cover on it. It would have multiple stages, just like a jet engine. It would run hot water that would flash to steam, that would turn these turbine blades, and on the back end of this would be a generator to be able to take this rotation and generate electricity from it. Then the excess water would be taken out. It might be run through a binary plant, or it might just be run through a condenser to be able to condense it and turn it from steam into water and then repump it underground. So that's the basic format. So steam turbines, a generator behind it, cooling towers for the water that comes out of this, and the turbine hole being existing on property with hot water being fed into it. So to be able to run that, we have to get fluids out of the ground. So the well heads are very nondescript. They supply water on these pipes. They're typically quite large diameter pipes, 4 to 8 inches perhaps, but they're also insulated and are much larger than the original piping, because you want hot water that you take out of the ground to arrive at the turbine holes hot also. And so we can calculate the rates at which we can recover fluid by looking at the recovery from individual wells. Water will be supplied. These wells are typically of the order of 4 to 8 inches in diameter, typically larger diameter than petroleum wells, because you need to get more volume or mass of fluid out of the ground because its energy density is much less. So if you go by value, a current barrel of oil is 120 and rising. A barrel of 200 degrees centigrade water is probably worth 20 cents, less than $1. So the big mismatch in value of the products drives the requirement to get a relatively large volumetric flow rate out of it. So if you look at flow to a well, you can look at a single well. We talked before that the geometry of this would be a cap rock with a reservoir, wells going through the cap rock to be able to get to the reservoir, and as a result of that, being able to both recover and re-inject from these components. So recovering at some volumetric flow rate, running it through a plant to get the energy out of it, and then introducing it at Q. This would be a cap rock. This would be the reservoir. So this keeps the pressurized and insulates the fluids from losing too much heat. Most of the heat loss would be by convection, not by conduction. So it keeps the reservoir hot. Within the reservoir, if it's cased, the casing would be perforated to be able to recover the fluids, which would flow to the production and from the re-injection wells. And if you look at the pressure distribution, it's not very good. You get drawdown so this might be the original water level or pressure level within the cap rock. This would be what we referred here to as P2, the pressure that is being re-injected, and this would be P1. And so I guess in some respect this would be a pressure distribution with space and with pressure. So you depress the pressure in the recovery well bore. You wouldn't want to depress it into the reservoir because the reservoir would desaturate. You just depressurize it within the caprock. And after you've done whatever you're doing with it, you'd recondense it and re-inject it. And so what we can do with this is look at merely a tributary area of the reservoir. So this goes out, I guess in plan view, it would look like this. This would be a flow line that would link the injection well to the recovery well. Other flow lines would look like this, etc. And these would be, if you think of this as equipotentials or equal pressure regions in plan view, it would look something like this. So this is a neutral boundary. It's neutral in that the pressure on this boundary should be exactly, this would be half P2 minus P1, which would be this pressure here. This would be P2, this would be P1, and this would be exactly halfway between that. And so we can isolate a single slice of the cake which represent this behavior. The solution to this is pretty simple. We can use Darcy's law, permeability, viscosity, pressure gradient, which is defined locally. The pressure gradient above here, if we draw it on top of this, would look something like this. So this is the pressure change. This is the radius over which it occurs. This is always true everywhere on this curve, but of course the gradient changes as you go along this curve. And so if we have Darcy's law, we can apply continuity because we realize that if you draw a section across any part of this slice of the cake, the volumetric flow rate across this Q has to be the same. Q here is the same as Q here. And so if you multiply Darcy's law by an area times the velocity across the surface, this product has to be constant no matter where you do it here or here or here. So if we write this, if we substitute Darcy's law in here, we substitute the area in here. The area, this length here changes as a function of radius. So this circumference here, if you draw a circle here, not bad. This circumference here, this would be 2 pi r around here. If it was a different r, it would still be 2 pi r. And so 2 pi r is the circumference. The height of the geothermal reservoir is this distance here. Which is this here. The depth to which the well would penetrate. This would have a low permeability. This would hopefully have a high permeability. This permeability here is the permeability here. And if you take these and multiply out the flow rate, which has to be constant, it's just given by this. The variables here are R and pressure. And so if you separate those terms, so if you separate radius, which exists here, both over to the left-hand side, and this also, and rearrange, you get this relationship. This goes to here, this goes to here. And if you integrate it between two limits, one limit is the internal radius of the well, the external limit is the external boundary. This boundary, I guess the main thing is that this is a constant pressure boundary that we have here. And so we can define each of these by those two pressures. And if we do the integration and we substitute limits, we get log R2 minus log R1, and we get the straight pressure change at the outer boundary minus the pressure at the internal boundary. And if we rearrange this in terms of volumetric flow rate, we end up with this. So that simply gives us how much volumetric flow rate we get if we know the permeability, if we know delta P between the external and internal pressures, and the distance between those, between the external radius and the internal radius. So if you pull some reasonable numbers out of this, to have a viable reservoir, you need something around a millidarcy plus. So this is a millidarcy. Geysers would be about 200 degrees centigrade. So the viscosity of water at that is something like 10 to the minus 4 Pascal seconds. It's something like 10 to the minus 3 Pascal seconds at 20 degrees. So it is less viscous by an order of magnitude at 10 times warmer. The length, Josh asked the question about separation between wells at the geysers, and we did the calculations. So I think we said that this is something like 500 meters. And I think here this is quoting that magnitude as being actually L is, so this might be 1,000 meters or perhaps 250 meters at the geysers. Delta P, well, we mentioned before that when you produce from one of these reservoirs, you don't want to draw down the pressure into the actual reservoir itself, because you'll end up desaturating a portion of the reservoir, which then is a reduced cross-section for the water to flow across. And it also means that you're desaturating part of the reservoir and you're not getting fluid flow through it, and so you're not getting the benefit of taking heat out of that. And so you'd keep that within the reservoir. So typically, the geysers, this might be of the order, we've looked at the cross-sections before, this might be of the order of 1,000 meters. So in terms of the pressure change would be 1,000 meters times the unit weight of water. The unit weight won't change if it's still liquid. It certainly won't change as much as the viscosity will. The well spacing might be of the order of, well spacing by 2 is the radius. So this distance here is spacing over 2. And R1, typically large diameter wells, because you need to get a large volumetric flow out of it, because it's not as valuable as hydrocarbons. So that's kind of the challenged economics of geothermal systems. Hydrothermal reservoirs are great because you know where they are. You don't have to drill very deep to get to them, and you potentially have high throughput because the permeability of the reservoirs are great. The economics of EGS are much more difficult because the permeability is low and you have to make it high, typically much deeper, because temperature gradients are not trapped at high elevation within the stratigraphy as they are in hydrothermal deposits with a cap rock on top, and so you have to get large flow rates through it. So getting water to the well is rate limited, I guess, by the permeability and the viscosity of the fluid. Once you get it to the well, then you have to deal with parasitic losses. So frictional losses in the well bore are something that has to be accounted for. So it'll come in at some velocity. It will go out at the same velocity if the cross-sectional area of the pipe doesn't change. This would be the depth of the zone. So I suppose typically here, below the cap rock, you'd have a region which would be perforated, still be cased potentially rather than open hole. And so this would be the part that is gathering water and then sending it up to the top at some volumetric flow rate. So this would be Q. Q would be equal to the cross-sectional area of the pipe multiplied by its velocity, volumetric flow rate. And so if you write Bernoulli's equation between the downstream part, which is above, and the upstream part, which could be at the bottom of the well, it could be at the bottom of the casing, kind of a judgment call as to how deep L would be. And I guess the other thing we should make clear is that the coordinate system is with Z positive upwards. Then you can just write the behavior in terms of simple relationships. So the velocity is equal to the volumetric flow rate divided by cross-sectional area of the pipe, or Q is equal to the velocity in the pipe multiplied by its area. The length is just the difference between the top and bottom of the pipe. Bernoulli's is written between upstream at the bottom and downstream at the top. Elevations are at the base of the well, at the top of the well. Velocities along the length of the well will not change, and so these two terms will drop out. And you have to balance this with frictional losses along the pipe. So in other words, flow along the pipe, and therefore the frictional losses that result from this, and also, I guess, in terms of maybe putting a pump in the circuit and putting energy from pump. So this is pump losses, or pump. And this is friction losses. And so if you get rid of these parts which stay the same, you're left with this. And so typically you'd know both of these. This might be close to atmospheric. This might be close to the reservoir pressure just by the head of water, which is pretty straightforward to calculate, or you could measure it. The elevation difference between where you're siphoning off the water and where you're discharging it on the surface. Once you get to the surface, most of the motion of the fluid will be horizontal. So this might be 1,000 meters, but once it gets to the surface and goes through the different parts of the plant, probably doesn't change in elevation by more than 10 meters. So that's 1% of the elevation. And you'd want to be able to size the pump for the given magnitude of flow that you get. So you typically might choose a volumetric flow rate that you want. So if you choose the flow rate you need, then from that, for a given diameter of a pipe, you would know the velocity it needs to travel at. If you know the length of the pipe, your choice of diameter, gravity on this planet, if you know the Reynolds number from that velocity, which would be equal to a velocity times a characteristic length times a density of the fluid times the viscosity of the fluid. If you know from this velocity here what a Reynolds number was, then you know from that Reynolds number some friction factor, which you'd get depending on how rough or smooth your pipe was. And if you know what that is, then you know exactly what your friction factor is. In other words, this. And if you know what your friction factor is, you can put this into this equation. If you know that, then you can calculate this. If you know this, and you know the volumetric flow you want, you know the density of the water, you know gravity, and then that gives you finally power. Not power from the reservoir, but the power you have to apply to be able to raise this heat, which of course is a parasitic loss which gets debited against the energy that you take out and sell as electricity. So this would be in watts. Yeah, watts. So that's Newton meters per second. So this isn't really a course on the surface plant so much as the subsurface, but this would allow you to calculate how much fluid you can get to the well for a given drawdown in pressure that you apply to be able to do it. And once you're getting that volumetric flow at the well, the next thing to calculate is how you get up to the surface by pumping it, and to size the pump if it's not artesian in being able to draw it from the surface. So that then gives you a certain amount of fluid that is capable of being brought up. This is an opening. Brought up to the plant. It'll be brought in these individual insulated pipes, and it would go into the plant to be able to run through turbines and be able to convert heat energy into electricity, which means that it has to go through a couple of different conversions, each of which will reduce, by the conversion, will reduce the amount of energy that's available. So this is the power that comes out of the ground. So I guess this would be a heat rate in terms of mass flow rate times specific heat capacity times the temperature. The temperature it comes out of the reservoir versus the temperature it goes to on the surface, which would be 20 degrees centigrade at the best case probably. And this would be the power that comes out of the system. So the thermal power has a conversion from thermal power to kinetic energy that goes into the turbine. And then there's an efficiency of the kinetic energy of the turbine in converting that through a generator into electricity. So there are two conversions that are important. If you remember, it's a long time ago now, and I'm not sure whether I can do this so easily. I don't know. Let me do this so I can maybe run it back faster. Okay. Yeah, fine. That's faster at least. You remember one of the things we looked at second time we had the class was this conversion table to be able to look at the magnitudes of different systems. This was one of them. This had some efficiencies, typical sizes of some behaviors. And so this is, thermal to mechanical. And so this is going from the power that we have in the hot water, flashing it to be able to get mechanical energy in terms of rotational energy in the turbine. Is something like you go from 100% to 45% or so. And then in converting that mechanical energy to electrical energy is quite efficient, maybe 99%. And so these are the two conversions that we have to go through. And so if we look at that in terms of going back to this, I can go. Just to make that point. So those two sequential conversions, which I'm trying to get to, I guess it's in here. Go back. Oops. So these two conversions are these. So the first one, it turns out, is, so we saw before that it's about 0.4 to 0.45. So it's not clear why this would be 0.85. Well, it turns out that actually the proportion of steam has an impact. And so the more steam you have, the more efficient this conversion, and we'll talk about that again. And this one, actually, from what we've just seen, this may be 99% efficient, maybe larger than this. And so this one is quite large. This one is potentially smaller. So the mechanism by which this is done, and Greg will talk about this in terms of how we create hot water into electricity is that you recover it from the subsurface. It's hot. You put it into a steam separator. The steam separator takes out the water by allowing the buoyant convection of the steam to rise to the top, which is then put through a steam turbine, flashed in the steam turbine, collected, condensed, compressed, and then re-injected as cooler, not cold, but cooler, back into the geothermal reservoir. And the liquid that you take off that you can't otherwise use, you return also directly to the reservoir at some elevated temperature to be able to maintain the volume of fluid in the reservoir, which you want to use in the future, because it will track from the injection well to the recovery well over time. And so this is just to ensure the longevity of the reservoir. So what you could do is also, with this hot water, instead of, since you can't flash it because maybe it's not above the boiling point of water at atmospheric pressure, what you could do is you could run it to heat up a heat transfer medium that boils maybe at 30 degrees centigrade, such as isopentane, which then flashes to steam and then could run through a closed system generator completely separated from this very large turbine which would exist on site. So that's the mechanisms that we'll talk about. So this idea is here. It goes into a steam to water separator. It comes in at some mid-level. The steam buoys to the top and then is taken out to the generators. The water sinks to the bottom, is siphoned off and is re-injected or maybe run through a binary plant. So we talked about the efficiencies of these. Turbine efficiency in converting the steam to mechanical energy, rotational mechanical energy, is given by this relationship. This is the proportion of steam that's present in the system. And so you could imagine it all flashing to steam, in which case this term is 1.0, decimal term, and this term would be 1, and the efficiency would be equal to about 85%. And alternatively, if it's all liquid, then this term will be 0, and this will be 42.5. This would be 0, and this would be 0.425. And so the efficiency is determined based on the energy, the enthalpy that's present in the water. High steam enthalpy would mean that it's available at a much higher energy. And we know that systems operating at higher temperatures are intrinsically more efficient. So what we're going to use is we're going to use the Carnot cycle. We've talked about it already. We can talk about temperature versus entropy. And the idea is that we take fluid, we add heat to that fluid. We already naturally add heat to the fluid because we bring in hot fluid, and with no change in pressure or temperature, we allow it to flash to steam. Once it's flashed to steam, we can get work out of it by its expansion. Once it's expanded, we can take heat out of it to be able to condense it and to then apply compression to be able to get it back to its initial state and then reintroduce it back into the reservoir. So that's the cycle that we're going through. So in going across this system, we're taking it out of the reservoir at some high temperature, and we're putting it back into the reservoir at some lower temperature. This isn't necessarily the return temperature because we might condense it, but this would be the temperature it comes out of the turbine at. And so the efficiency of that system is the recovery temperature of the geothermal fluid and the base temperature that it goes to in the atmosphere at the ground surface in the geothermal field. So this defines the efficiency of that system. The energy that we take out of it is the amount of thermal energy that is taken by us bringing in hot water. So this limb of it relates to the the heat rate into the system. This part is the amount of work that's removed from that system into which heat has been taken, and the rest of the limbs kind of follow that. So if we look at the heat that goes into the system, it's really the change along this limb, the enthalpy that we have at A versus the enthalpy we have at B. This is the term that we used for that before. It's in kilojoules or joules per kilogram. This is enthalpy. Which is pressure divided by density and internal energy per unit mass. That's what enthalpy is. And so we know that the energy coming into the system, which we aren't doing work on, is the change between these points and these points. This is in entropy, but we could also think about this plot having this axis defined in terms of enthalpy. It'll look very similar, as we'll see in a moment. And so we can define the enthalpy in a system at any particular point by being able to look along a line at a given temperature and seeing where it lies upon this line. So at this point here, it'll be 100% steam. And at this point here, it'll be 100% liquid. And so in going from the inlet behavior to being whatever the enthalpy is at this point, this is the trajectory that we take from inlet to recovery. So we can use that to calculate how much energy we'll get out of the water, which would be, of course, not of course, but would be this amount of power we get out by flashing it. And then if we know what this power is and the two conversion efficiencies, we know how much electricity we'll get. It's always going to be less than the thermal power, because these are net losses, series losses. So to be able to find this value of enthalpy here, we can use the magnitudes of the enthalpy of the liquid at that particular temperature and the enthalpy of the steam, and this is the proportion of steam that's present within that system. Proportion of steam, the mass proportion of steam multiplied by the entropy of steam or the enthalpy of steam, and this is 1 minus the mass of steam, which would be the mass of water multiplied by the enthalpy of the liquid water. So those are the basic relations that we'll use. This example comes out of Glassly, and it just chooses some numbers and then uses it. So this would be roughly supercritical water at 170 times atmospheric pressure. So a bar is 0.1 of an MPa, so this would be 17 MPa. This would be ambient temperature, not today, but typical ambient temperatures in places like Nevada, which would be the baseline lowest temperature that you can reduce to without cooling it with some other means. And these pressures would be in gauge pressures. So 0.04 of a bar is 1.04 bars absolute pressure, right? So if you look at for this system, water's coming into the turbine at 352 out of the reservoir, and it's coming out of the turbine at 30 degrees centigrade at these particular pressures. So what we can do is we can go to a figure like this, but instead of using entropy, even though we want to have an isentropic behavior would be coming vertically down here, no change in entropy. So on this vertical line here, the entropy remains constant at this value, but our steam tables are written in terms of enthalpy. So we have to use this isentropic behavior to convert it into the changes in enthalpy, which are what we want to determine. So if we know it comes in at 352 degrees centigrade, this relationship of T1 over T2, T1 relative to T2, is written in terms of absolute temperatures. So 273 is 0 degrees centigrade. So this is T1, and then this is T2. So if you take those values, the maximum efficiency of this machine in converting from thermal energy into the next form would be equal to 0.52, so 50% efficient. If we look at the water coming into the system, into the steam tables, it comes in at 350 and at 170 bars. So this is 170 bars would be, this would be 200. So this is 170 going across here. Comes in here. This is liquid. This is 100% steam, would represent the change across there. So at 352 degrees coming in, at liquid enthalpy would be equal to this value here, which is 1690, I guess. Which is this value here. In going across here to steam, this would be this, which is 2548, which is these two values here. And so this magnitude here, representing this, would be HB. This would be how the fluid comes into the turbine that's coming out, having the heat added to just regular water. It's gained this in the reservoir, and in the reservoir it comes into the turbine at HB, and that's what's available to convert into whatever enthalpy it has at this lower temperature, which is going to be 30 degrees centigrade. And so its journey from these 2 points here is going to be going to 30 degrees. So 50 degree behavior, 25 degree behavior. So 30 would be partway between those. So the enthalpy of water at 30 degrees centigrade would be equal to whatever this is. And this is 126 kilojoules per kilogram. And the other magnitude would be whatever this is here. The lower one would be 2556. So these two ordinates here and here represent this and this. And this, these two ordinates here represent this and this. So these are the enthalpies, liquid and steam at these two different temperatures. That's all. And so what we're going to do is we're going to move from this point here, where we know exists, it's this, and we're going to find out where we end up as we go down isentropically, so no change in the entropy of the system as we go down here. So notably, this is written in terms of entropy and temperature, bless you, and not enthalpy and pressure. And so what we want to know is where on this lower curve, if we reduce ourselves without changing entropy, where on this lower curve we exist. And so if you draw this curve here, instead of pressure versus enthalpy, as pressure versus entropy, isentropic means the entropy doesn't change as it goes from one temperature to another. So it has to track along this curve here. And in doing that, it will end up at this point. And we'd like to know exactly what the value of the steam content is that represents this point. We could do it by realizing that this is 100% steam and this is 0% steam, and just dividing this up to 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%, which isn't bad. This would be just less than 60%. Or we could use this expression, which we've also seen before, that says that the entropy at this particular temperature of 30 degrees centigrade is equal to the steam content at the entropy of steam and the liquid content, which is this term together. This is again the steam content. 1 minus the steam content is the liquid content, multiplied by the entropy of liquid. So in other words, this portion here. So if you take the portions out from here, so this would be, I see it 0.4. I'm just reading it off this upper part here. This is this point here. And this point here, if you go down, is something, this is 9. So this is 8.4. Yeah, this is 8.4, this division, 8.89. So this is, just to follow this, 8.452. And since we also know the entropy at this point, just by measuring it off, 4, this would be 5, this is 5.4 here. Yeah, 5.4. No, 2, 4, no, this is 2. So this would be 4, 8, 5. So this would be 5.2. This would be 5.2. And so it's just less than 5.2. And so this is the magnitude here. And so if you solve this for the only unknown in here, which is the steam content, you end up getting 0.59, which isn't very different from you looked at this as 10%, 20%, 30%, 40%, 50%, 60%. So this is 0.5. They're just two different ways of getting the same number. So we know then that now, if we write this expression in terms of not entropy, but enthalpy, this is the steam proportion. This is the steam proportion. You put in these magnitudes of H sub C. And so this is equal to, so we know exactly what this value of enthalpy is 1560. So it's this value that would exist here at, so this is 60% steam, and so this magnitude would be here. So the enthalpy that represents that point here would be, I'm taking it as 1560, which is this. You can get it from substituting 60% into this and the values of these magnitudes of this and this, which are these two values here. And so we have H sub C, and we have the difference between that and 2548. So in other words, we're going from this point here where it comes out of the ground to this point here. This would be what we called before H sub B, and this would be what we called before H sub C on this Carnot cycle. It's isentropic as you go down here, but when you plot it against enthalpy, this track is no longer vertical. It's actually this track here. And so the punchline is, if we know this point here, if we know the enthalpy at this point here, we can calculate the difference between them, which is what it comes in from the geothermal reservoir at H sub B, what it goes out of the turbine at H sub C, and that's approximately equal to 1,000 kilojoules per kilogram. So the maximum amount of work that we get out of that system is going to be 1,000 kilojoules. about 1,000 kilojoules per kilogram, which is 1 megajoules per kilogram. And so this now is the magnitude that goes down here. It's the amount of power that comes out that's flashed to steam, and it has to be run through these two efficiencies. First efficiency is the conversion from thermal energy to kinetic energy, if you like, how efficient the turbine is. It's 1 plus the steam proportion divided by 2. So 1.6 divided by 2 is about 0.8, which is 0.85 times 0.8. I don't know what that is exactly. It may be about 0.8, probably about 0.7, right? Bet you it's about 0.75. You could do, I guess I could do the calculation here. 0. 0.7. So it's about, whoops. And so, and therefore, and then so this is kinetic to elec. This is thermal to kinetic, the rotation of the spindle. And this probably isn't right. This is 0.99. Yeah, fine. There's nothing that we saw. There was it was 98 to 99%. And so if you multiply the total, so this would be 0.7. Make it a bit neater. This would be, no, fine. Yeah, fine. So this is 0.7. This actually is probably closer to 99%. And so if you multiply those together, this is essentially, so it's about these two parameters together, in our particular case, is about, because this is almost 1 and this is 0.7, then combined the product of these is about 0.7. So if you assume that we've talked about the payback amount required is of the order of, typical value is 100 kilograms a second to be able to pay for the wells in terms of 5 megawatts electrical, is 100 kilograms a second, maybe at 100 degrees centigrade differential. Here, if we have 100 kilograms a second at a differential of 320 degrees Kelvin, then if you multiply 1,000 kilojoules per kilogram times 100 kilograms a second, then the net output from this system is something like 100 megawatts thermal. If you multiply this by 70% efficiency for going from thermal to kinetic and kinetic to electric, then you'd end up with 70 megawatts. Much bigger than the 5 megawatts electric that we wanted to get from EGS. So this would be electric, this would be megawatts thermal, and so a big number. And the reason is because it's a huge drop in behavior, because it starts out at very high temperatures. And so the net result of that is there's a big temperature drop, and therefore the efficiency of the system greatly increases as we go to higher temperatures. And that's reflected in this much larger value of efficiency that we get as we have a larger temperature drop between recovery temperature from the reservoir and background temperature as we pull it out into the subsurface. What am I going to do? So the other way we could do it, so that's a way to be able to calculate how much energy we get out of the system. Obviously, in addition to this power that we get out of it, we'd have to subtract off the parasitic losses. So we have to pump water maybe to the well and raise it up a couple of kilometers to get it into the turbines. So that would be a net loss in the system. And we also have to condense it, compress it, and pump it underground potentially under pressure. So those are two parasitic losses that would end up being in the energy budget that would detract from the amount of power that we recover from the reservoir. The other idea is that we can do dual flash. And so the idea is that when you see these plants, I don't think I have a very good picture of it, but when you see these kind of cooling plant, all this is the geothermal water perhaps going around this in a radiator with lots of surface area, air being pulled up just like the air being pulled through a radiator either by the motion of a car or by the fan behind the radiator that brings water, that brings air through the radiator when it's static, not moving, and transfers the low temperature of the air to the high temperature of the water, and then re-injects the water somewhere else in the geothermal field. The other use when you see these things is that the circulating fluid, instead of being water, is actually some fluid with a lower boiling point than water, such as isopentane. So the idea is that when you bring water to the surface, you circulate that water, which might be colder than 100 degrees centigrade, through a heat exchanger. That heat exchanger has isopentane completely separated from the water in its own circuit, and it warms the isopentane, and that pentane goes in and runs through a turbine, is collected as isopentane, condensed, and put back in the system, all the time separate from the water. So sometimes when you see these cooling towers, the liquid that's running around in these is isopentane, which is being cooled by the ambient temperature at 20 degrees centigrade or 30 degrees centigrade by air, and then cooled and recompressed and then pumped underground. And so in those particular cases, what that is following is this lower limb on the Carnot cycle. So it's coming in as vapor, it's being cooled by the air temperature that's adjacent to the radiators. So you're taking heat energy out of it and cooling it, and then you're providing work into it to be able to compress it. So it goes from a gas here to being a high density gas, which is then compressed and is then flashed to isopentane vapor, run through a turbine, and then cooled. So that's kind of the reverse cycle. So you can do some calculations like that. I'm not sure we need to do it, but we need to be able to just understand the system. This is a much better schematic of exactly what it is. So the water comes out of the reservoir at whatever temperature it comes out of the reservoir. It goes into this circuit, which is this crosshatch circuit. This is completely separate from the other circuit. It goes in at 165, gives up some of its heat to this other circuit, and goes out at 60 degrees. So it's lost 95 Kelvin as it's gone through here. So that 95 Kelvin has gone to raising the temperature of the isopentane to 135 degrees centigrade. I think the boiling point of isopentane is something like 28 degrees centigrade. So it comes in here, it's under pressure, it's flashed to a steam, it goes through the turbine, it runs this turbine, and then exits at 85 degrees centigrade. It's condensed to 35 degrees centigrade. So on the Carnot cycle, that's here. So this is temperature or pressure. This is enthalpy. So this point here is going into, this would be our HB. This would be our HC. So HB goes adiabatically down to here, and then is compressed by first cooled and condensed. So this stage here would be this, as it goes across here, and then this stage up here would essentially be this. It comes in at some pressure, and then the pressure is increased as it's pumped to be able to compress it, and it goes through the same cycle again. So this cycle of isopentane, water and the isopentane are completely separate from each other, and we're representing these two limbs. I don't know if we called it HD. This was certainly HA. Represents this limb and this limb. So taking heat out of the system, which is Q, which is this point here, and putting work into the system, which is compression, which is this here. So that's it. And so that means that so long as you have a fluid that's circulating here, which is actually has a boiling point which is below that of the water out of the reservoir, you can always generate electricity by flashing it. And so this, I guess, this calculation, I don't think it's really important, but if you work out how much energy you can get out of this system, then you can calculate the amount of energy you have to supply to cool it. So if the specific heat capacity of the isopentane is 2.3 kilojoules per kilogram per degree Kelvin, and you're running it through a pump at 20 degrees, 20 kilograms a second, then this is just mass flow rate, specific heat capacity, and the temperature change. And the temperature change is going from 135 degrees centigrade to 85, which is a change of 50 degrees centigrade between these two temperatures. So this is the temperature change. So this is the amount of energy you need to supply to the isopentane, 2.3 megawatts at 100% efficiency, and you have to supply that energy by this. So this would be, the heat rate would be equal to the mass flow rate of water, geothermal water, times the specific heat capacity of water times the temperature change of the water. And the temperature change in the water is coming out of the reservoir at 165 and going back out of the system at 60. So this would be that final part. So you need to balance the heat rate coming out of the water and going into the isopentane with the heat, with the energy of the isopentane as it goes around the circuit. And they'd obviously be balancing. And that's right on our witching hour, and which is a perfect segue. So these energy conversion changes, not my speciality, mainly geological side, but this is the relatively straightforward mechanics by which they work through. So single flash takes hot water out of the system. It's easier to show on this. Hot water out of the system, flashing it to, taking it into, adds this limb doesn't exist. It comes out with heat supplied into the system. This heat is flashed, it does work, it's cooled by condenser, compressed, and sent back to the reservoir. Then new water comes in at some increased temperature and goes through the same cycle. So single flash goes from this limb to this limb and represents the amount of energy that comes out of the system by going on this trajectory. The binary cycle takes heat out of the system by condensing a fluid, compresses it, and then flashes that separate fluid, runs it through a turbine, and then repeats the cycle. So they can all be represented on this Carnot cycle just by representing different stages. These binary plants, Greg Bignell will talk about them next time. I don't know if he works still for baseload power, but they sell these things. And they're typically relatively low output. Maybe they work at a couple of megawatts or something, maybe 10 megawatts. And he'll actually show some plants that have outputs at those magnitudes. I don't think I have them here, so I'll leave it there. Okay.